We're solving linear second-order constant coefficient differential equations, homogeneous because they're equal to 0. So they're all of the form a y prime prime plus by prime plus cy equals 0 for some numbers a, b, and c. We know what to do. We get our auxiliary equation. We solve for the roots of the auxiliary equation, the eigenvalues, the lambdas, the roots of the auxiliary equation. We can either factor that auxiliary equation or use the quadratic equation to get the lambdas. And we've got three cases. Either we get real and different eigenvalues, we get real and the same eigenvalues. I guess if the thing under the square root sign is 0, we get real and the same. If the thing under the square root sign is negative, then we get a complex conjugate pair of eigenvalues. That's what we're going to be dealing with in this video. So to real and different, some constant, we take C1 and C2 are the constants. We take a linear combination of the e to the lambda 1t and the e to the lambda 2t, if the lambda 1 and lambda 2 are different. If they're the same, we take a linear combination of e to the lambda t and t e to the lambda t. We need this extra t in front here if the two eigenvalues are the same. Now we're going to deal with a complex conjugate pair. Now before we start to deal with the complex conjugate pair, we have a notation issue. And it's really both a combination of an intersection of tradition and the fact we only have 26 letters in the alphabet. The a and b and c in my quadratic equation, those are the traditional a, b, and c that we pop in. A is the thing times the variable squared, b is the thing times the variable, c is the number. This a and this b in the complex number are not the same a's and b's from up here, but traditionally we use a and b also for this complex number. So this a and this b, what I mean by that is after I've got the eigenvalues and they're a complex conjugate pair, there'll be a number plus or minus I times some other number. The real part of the complex number is the a, the imaginary part of the complex number is the b. So this a and this b are not the same as this a and this b. That's my point here. So I'm at the stage then where we've got our differential equation, our second order linear constant coefficient homogeneous differential equation. We got the eigenvalues and we didn't factor it because we couldn't. We used the quadratic equation and we got this. We got lambda equals a plus or minus I times b. What do? Well, if I follow along, if I say, well, you know, a plus b ib and a minus ib, they're different. So I'll do the same thing as real and different. I'll just stack them. So this lambda 1 is with the plus, and this lambda 2 is with the minus, and I stack them on the e to the lambda t's, take a linear combination of the e to the lambda 1t and an e to the lambda 2t, just do what I did before. Let's see what happens. So I'm replacing the eigenvalues with what they are, those complex conjugate pairs. Now, I cannot leave it like this. Why can't I leave it like this? Well, I can't leave it like this because my question was given in real numbers. I can't give my answer back with complex numbers. So I have to deal with this e to the complex number. And we know how to do this because we saw this in another video. The first thing I'll do is distribute the t across and then factor out the e to the at. So here I've got the e to the real part t, and now I've got a linear combination of e to the ibt and e to the minus ibt. This is what we dealt with in the previous video. We know that I can change this linear combination of e to the ibt and e to the minus ibt into a linear combination of cos bt and sine bt. So what does that mean? Well, that means if I get a complex conjugate eigenvalue, this is my answer. This is my homogeneous solution. E to the at, e to the real part t, some constant cos imaginary part t plus some constant sine imaginary part t. How do I get the constants? The initial conditions. The line from here to here is just me redistributing that e to the at over this plus sign. So I could think of this as one little solution and another little solution. So my answer is a linear combination of little solutions. The little solutions, the y1 is e to the at cos bt, and the y2 is e to the at sine bt. We also saw in that other video that I can write a linear combination of cos and sine as a single shifted sinusoidal function. So I can write the answer as either, well, any one of these three forms. In any one of these three forms, what controls whether or not the homogeneous solution goes to zero? Because this is the thing we were concerned with last time. If, when we had two real and different eigenvalues, if they were both negative, as t went to infinity, the homogeneous solution went to zero. If one of them was positive, or both of them were positive, then it went off to infinity or minus infinity. Same conclusion with the real and identical. If this real eigenvalue was the same real and identical eigenvalue was negative, the homogeneous solution went to zero. Now, it's the real part that determines whether the solution goes to zero or not, whether the homogeneous solution goes to zero or not. In all three of these cases, if A, the real part of the eigenvalue, is negative, then e to the at goes to zero, and what happens to the sine bt? Yeah, it just oscillates up and down, or these two pieces oscillate up and down. They're dragged down to zero by the e to the at going to zero. So if the A, long story short, if the real part of the eigenvalue is negative, then the homogeneous solution goes to zero. So now that we can use as a rule for all three cases. If the real part of both eigenvalues is negative, if the real part of both eigenvalues is negative, now if they're both real, then it's all real part, and that fits our conclusion. If they're the same in real, then they're also fits our conclusion. If they're complex conjugate eigenvalues, then it's the real part that fits our conclusion. So that's going to be our rule. If the real part of both eigenvalues is negative, then the homogeneous solution goes to zero. Otherwise, it goes off to plus or minus infinity, or in the case of this complex conjugate eigenvalues, it oscillates off to infinity. So, oh, that's another thing. We get oscillations because we get trig. We only got trig because of that Euler's relation. So when we see complex conjugate eigenvalues, we want to associate that with oscillations, with trig. When I see trig, or when I see oscillations in a solution, like an upcoming spring problem where a spring is oscillating back and forth, or a pendulum is waving back and forth, anything going back and forth, anything oscillating, then I want to think about complex conjugate eigenvalues. We're going to associate complex conjugate eigenvalues with oscillations. Why? Because oscillations have to do with trig, and the trig showed up with complex conjugate eigenvalues because of Euler's relation. I guess let's do an example. We did a lot of investment in the previous video on getting these solutions to be equivalent, showing what e to the I theta was, and so now that investment will pay off. Let's solve and graph this solution. Okay, first thing, we got to find the eigenvalues. So I need the auxiliary equation. Let's put it in here. So everything starts off the same. I can't factor this, so I have to use the quadratic equation. So I get the real part of the eigenvalue is negative 3/2, and the complex part of the eigenvalue, the b part of the eigenvalue, is root 3 over 2. Right away, before I do anything else, I know that the solution as time approaches infinity of this differential equation goes to 0 because the real part is negative. Let's get that solution. Now I can write this in any of these three forms, but because they're asking me to graph it, I think that the one shifted sinusoidal function is going to be the easiest way to do it. So the real part is minus 3/2, and the imaginary part is root 3 over 2. And that's y homogeneous. Now all that's left to do is get those two constants, but really getting the solution in the right form is that straightforward. Once I get the eigenvalues control the whole behavior. I just need to get what's the phi and what's the a. How do I get those two constants? Initial conditions. Our first initial condition is that y naught is equal to 0. So when I put t in for 0, I get 0 out for y. So when I put t equals 0, e to the 0 is 1. When I put t equal to 0, this part disappears, and I get a times sine phi is equal to 0. Well, that means that sine phi is equal to 0. That means that phi is equal to 0. Again, it's just going to be two equations, two unknowns. Sub in the first equation. Now, I need the derivative here. So I'm going to differentiate this function. I already know that phi is equal to 0. So if I differentiate this function, I'm going to have to do product rule. Take the derivative, set it equal to 2 when t is equal to 0. E to the 0 is 1, sine of 0 is 0, e to the 0 is 1, cos of 0 is 1. So I get a is equal to 4 over root 3. I knew that phi was equal to 0. So here's the solution to this differential equation that goes through the point 0, 0, goes through the origin with a slope of 2. Now, the sketching part. I'm drawing this. For me sketching it, I'm just going to go and ask the machine to sketch it. And here's the graph of this solution. Well, this is the proper graph. The computer's drawn a nice graph for me. I can see that this function, this 4 over root 3 e to the minus root 3 over 2t, that's this what I'm calling the amplitude envelope. That's what's squeezing this trig function down. This sine, that sine function of itself, this just sine function, this just sine function goes up to 1, down to minus 1, up to 1, down to minus 1, starting at 0. This is its amplitude, and its amplitude is being squeezed down to 0. So it's oscillating, but getting squeezed down to 0. So we can also tell some other things. I know that all of the oscillations are captured in this sine function. The period of a normal sine function, just sine t, would be 2 pi. So in our case here, we can have a period function which would be equal to 2 pi divided by the b value. So it's a formula divided by the b value. The b is what's in front of the t. 2 pi. So in our case, that's the period. So we can get the period of oscillation, the length from peak to peak. I can't really see because it gets too small here. Some of the things, though, that we can see from this graph. As soon as we got the eigenvalues, right here, as soon as I got the eigenvalue, I knew because the real part of the eigenvalue was negative, that it was going to go to 0. Because I got complex conjugate eigenvalues, I knew it was going to oscillate to 0. I also, from the initial condition, knew it was going to go through the origin, and I knew it was going to go through the origin with a slope of 2. So I could have drawn it. I know it went through this point at 0, 0 with the slope of 2, and I knew it oscillated down to 0. So I could have given a rough sketch, even with its period, right from this step. I could have drawn a hand-drawn rough sketch of that picture as soon as I knew the eigenvalues. So we did, we tried to up here make it make the solutions to these differential equations, these linear constant coefficient homogeneous differential equations, when I got complex conjugate roots or complex eigenvalues, we tried to make it the same as the other two cases. And we did, but trig popped out, so we got oscillations, and with oscillations we get a period of oscillation, and that's a new formula that I get. It's 2 pi divided by the b value. The 2 pi divided by the imaginary part of the eigenvalue. Let's do another solution, or let's do another equation here. We got our auxiliary equation, our eigenvalues are complex. What can we tell at this stage without doing any other work? We know that the solution goes to 0 as time goes to infinity. We know the period of oscillation, it oscillates, it's complex, it oscillates down to 0 with a period of 2 pi divided by 2 with a period of pi. We already know that. To actually write out the solutions, I have 3 forms. Let's use this form right now. I don't have any initial conditions, so I can't figure out the C's, but I have the A and the B, the real part -1, the imaginary part 2. So our answer then becomes a linear combination of these two shrinking trig functions, let's say. Done. We can't find the C's. Let's do another example. This one has initial conditions. They're not asking me to graph it, although the graphing's not too bad. First thing I need then is auxiliary equation. The auxiliary equation, the only difference is here, that's a 3. Solve the auxiliary equation. Now I've got the eigenvalues. So what do I know? The eigenvalues are negative, real part, negative real part, so the solution eventually approaches 0. It oscillates with a period of 2 pi divided by root 2. We have initial conditions, so we can figure out the constants. Let's go and choose, let's choose this form. The imaginary part is root 2. The real part is -1. All I have to do now is get these constants. How do I get the constants? Initial conditions. Let's invoke the initial conditions. The first initial condition is it goes through the point 0, 1 with a slope of -1. So when I make t equal to 0, the sign is 0, so this whole piece disappears. The cos of 0 is 1, e to the 0 is 1. So actually, you just get that k1 is equal to 1. So now I can write this solution out. And I know that k1 is 1. To use the second condition, I need to take the derivative of this. So I've taken the derivative. Now I'm going to sub in t and set the derivative equal to -1. When I sub in t equal to 0, let's copy this down. When I sub in t equal to 0, sine of 0 is 0, so this piece and this piece disappear. Cos of 0 is 1. E to the 0 is 1. So it looks like k2 is equal to 0. So here we have the solution to this differential equation that satisfies these two initial conditions. When t is equal to 0, we get 1 out. If we differentiate this, we get the slope, has the right eigenvalues. We can now, I go up to the top then, we've got this completed. We can solve all of the equations of this form, whether I get real and different eigenvalues, real and the same eigenvalues, or now complex conjugate eigenvalues. If we get complex conjugate eigenvalues, we have a period of the solution, 2 pi divided by the imaginary part of the eigenvalue, the b. Now in all these cases, our real part of the eigenvalues were negative. Each one of these examples, the homogeneous solution went to 0 because the eigenvalue always had negative real part. Do they always have negative real part? No, sometimes they have positive real part. But one of the things we noticed of our examples is all the coefficients, the a, the b, the c in our equations, the a, the b, the c in our auxiliary equation, they were all positive. So let's take a minute to show that when the coefficients are positive, that the eigenvalues always have negative real part. So let's go back up to here, because this is the general case. This is the general case. These are our eigenvalues. And I want to show that if A and B and C, this A, this B, this C, are positive, then the eigenvalues are always negative real part. So we've got our 3 cases. Let's do the easy case first. If I have real and the same. If I've got real and the same, then the thing under the square root sign is 0, so my eigenvalues are minus b over 2a. They're both minus b over 2a. They're both negative. So if a and b are positive, the eigenvalue, I guess, because we're doing that middle case, that case where they're the same, is negative. We're done. What about if they're real and different? Well, if they're real and different, one of them is minus b minus this square rooted piece over 2a, so that one's negative. The only one I have to worry about then is maybe the other one, the plus one, is positive. Well, if the plus one, let's take this and consider the plus one. Well, the thing under the square root sign is b squared minus something. B squared minus something is less than b. Something less than b squared minus something is less than b squared. Square root of something less than b squared is less than b. Minus b plus something less than b, that's negative. Negative divided by a positive, that's negative. So if the a and the b and the c are all positive, all 3 positive numbers, and the eigenvalues are real and different, they're negative, so the solution goes to 0. Last case to consider. The last case to consider is if I get complex conjugate eigenvalues. If I get complex conjugate eigenvalues, I'm only concerned with the real part of the eigenvalue. Well, the real part of the eigenvalue is that, because that's what the I will be times by. So then the real part of the eigenvalue is also negative. I guess we're done. What have we said? We've said that if the A and the B and the C, if all the coefficients in our linear constant coefficient second order differential equation are positive, then the eigenvalues have negative real part. So I guess for our purposes, we can say then the solution, the homogeneous solution, goes to 0 as time goes to infinity, because the eigenvalues are all negative. Now we've got all 3 cases of homogeneous second order done.